respected faculty members, and my dear judges, very good evening. Myself, Dr. P. Baburao, working as assistant professor in EEE department in Veltech Rangarajan, Dr. Segundala R&D Institute of Science and Technology, Avadi, and located in Chennai. And main title is Non-NSTLBO based approach for optimal scheduling of hydrothermal generating units in regulated environment. In this, I'm going to explain about. So this is the main content: introduction, objective, proposed solution methodology, contributions, conclusions, and references. Main thing is, so nowadays power demand is more because of increasing of population. So our main agenda is to reduce the fuel cost for power generation, and particularly in terms of thermal. So my main the thing is I need to integrate the renewable energy sources as well as non-renewable energy sources. In renewable energy, thermal; in renewable energy, hydro, and non-renewable energy, thermal. So by these two integrating, the problem becomes more complex. Then, so here in non-renewable energy sources, especially thermal, the fuel cost is more. So here it is abundantly, though it is abundantly available. Because of this, we are generating the power, and the percentage of generating power from thermal is more. So here we have to concentrate on cost as well as emissions from thermal unit. So I need to reduce the cost as well as emissions from the thermal unit. That is the main problem I have faced. So I need to integrate the renewable energy sources, such as hydropower. Here I am going to integrate the available hydropower to generate the power by using hydro. Here I am integrating both the hydro as well as thermal, and the problem becomes non-linear mixed integer optimization problem. Here for this problem, main thing is the operating cost of hydro power plant is significant. Thus the problem of minimizing the operating cost is. So here most of the researchers have concentrated to solve these problems as single objective as well as multi-objective. But here in this, I am going to concentrate on single objective. It includes so several classical and mathematical analysis have been applied on this problem. Still, some convergence have been taken, divergence has been placing a vital role. So here, that's why I'm going to use non-dominated sorting teaching learning based optimization algorithm. This is a multi-objective optimization problem. Here, this optimization can be used as in terms of single objective. So what happens? So this optimization is used for the single objective. So main agenda is I'm going to reduce the fuel cost of thermal, of hydrothermal system for a period of 24 hours. This is the main thing. So for that, several problems have been applied still. Now I have applied improved teaching learning based optimization algorithm, TLBO I have applied, and now I am going to apply for the same problem as a non-dominated sorting teaching learning based optimization algorithm. So after applying, the obtained results have been compared with the previous results. So then I'm going to tell you that the obtained results have been predominant than previous. So this is the main thing. So the main objective is the proposed solution methodology has been applied on standard test system, that is 4 hydro, 3 thermal, IEEE standard test system, and for a period of 24 hours. So this is the main thing. The proposed problem has been applied. The proposed problem has been applied on standard test system. So that means proposed methodology. So I'm going to apply some methodology. and that the methodology named as non-dominated static teaching learning based optimization algorithm, and that is applied on a particular problem named as short-term hydrothermal system. This is the problem. And this for this I have taken one IEEE test system, standard test system, that named as 4 hydro as well as 3 thermal test system. And later, after applying the methodology, so the obtained results have been compared to the standard test systems. Okay. Now here, coming to the teaching learning based optimization algorithm. Here, this algorithm, before going to non-dominated starting teaching learning based optimization algorithm, first we will see the introduction of what TLBO. Here, in teaching learning based optimization algorithm, there are two phases. One is teacher phase, another one is learner phase. Here, in teacher phase, all the teachers, all the subjects, that means here, when it is arrived, means in the year of 2011, it is arrived. And it is invented by Mr. Venkat Rao. And the basic modes are, one is teacher phase, another one is learner phase. And here, through teacher is known as the teacher phase, and through learners, through the interaction of learners can be known as learner phase. This is the teacher phase as well as learner phase. See, a group of learners are considered as a population, and different subjects offered them can be considered as different design variables. This is the objective function for the optimization problem, fuzzy based. So your main thing is, so this is also called as modified teaching learning based optimization algorithm, and the main modification in the case of teaching learning based is, here in teaching learning based, only teacher phase and learner phase is available. But in case of non-dominated starting teaching learning based optimization algorithm, here fuzzy decision making feedback is included. So because of this, we will get n number of solutions for the particular solution. So for one, if you want to obtain one solution, it will generate n number of multiple solutions. In that, it will pick the best solution. And we will, whatever the result we are getting, that is the taken as final value. So the obtained value is compared with the previous value. So this is the thing which has happened in this. Now, so this is the formula, fuzzy decision maker. So this is the main thing is, this is the problem form. What is the main problem formation in this means? So here I need to reduce the fuel cost of the thermal unit for the problem of hydrothermal system. That means integration of hydrothermal makes the problem non-linear, in that the thermal value should be reduced with the help of increasing the value of hydropower. This is how the main thing is. Here F1 represents total operating cost. F1 is equal to summation is equal to T is equal to 1 to T, summation I is equal to 1 to JS, F of S and PS. Here PS is nothing but thermal power, and Fs is nothing but fuel cost of thermal. So this is the F1 is the total operating cost of thermal power unit, and this is the non-linear problem. Okay, and where A, B, C, D, and E represent the cost coefficients of the thermal units, and PSI minimum and PSI maximum represents the limits of the particular generator. Now, main constraint, this is the objective function. Now, main constraint is, so here we are having equality constraints as well as inequality constraints. Equality constraints represents the total power balance. That means hydro as well as thermal sum is equal to total demand plus loss. But here in this problem, I am neglecting the transmission losses. Okay, that means PSI is equal to PSI plus PHG is equal to PD. Okay, now, so this is the power generation of hydro entities can be expressed as this one. So this is a water balance. So in this we need to concentrate on a generation. So generation of hydropower. So first we need to generate the hydropower based on the availability of water in the reservoir. So first we have to calculate the reservoir storage volume with this equation. Later, and we need to substitute in the previous equation to calculate the value of hydropower. So already we see C1, C2, C3, C4 up to C6. These are the constant coefficients of hydro units. So those values can be taken from the base paper, and we can able to insert and we can calculate the hydropower. Once hydropower is calculated, we can substitute in this. Already we know the value of power demand, then hydropower, then we will calculate the thermal power. So the whatever the value we have calculated by obtaining the hydro, so then we can able to, so this is the power we have to generate with the help of thermal. So this is how we can able to justify. And this is the implementation of NSTLBO algorithm for the particular problem. And this is the test system. This table 1 represents the optimal generation of water discharge for four hydro units. That means Q1, Q2, Q3, Q4 represents water discharge for a period of 24 hours. And this can be, and this is the result. And table 2 represents the optimal generation of 4 hydro units as well as thermal units and total demand. So these are the results which we have obtained by applying NSTLBO based optimization algorithm for the test system. Finally, whatever the results we are getting, so we have calculated the manually, and based on that, whatever the value we have calculated, and we have compared with the previous results. So this, by using NSTLBO, we are getting a best solution. And these are the figures. So figure 3 and figure 4 represents optimal generation in terms of graphically. Previously, we have represented in the form of a table numerically. Now we are represented in the form of graphically. So main thing is, so for I have taken a short-term hydrothermal scheduling problem for a period of 24 hours, and it is taken as a single objective optimization problem. Main thing is we need to reduce the fuel cost in terms of thermal units. So I need to concentrate on improving the generation of hydro based on the availability of water. Then I can able to, if we want to concentrate, I need to use if these two are integrated, means the problem becomes more complex. So that's why I'm implementing the optimization algorithm to this particular problem. So whatever the result we are getting by applying the NSTLBO for this particular problem. So whatever the result we are getting, this is the best one by comparing the result which is obtained. So thank you.